so we're going to have a think about the behaviour of light when it travels from one material to another. And in this case, to keep it simple, we're just going to imagine that light travels from air into glass. So I've got a light ray which I'm firing in this direction here. You might remember that if we have a line at right angles, if this is my glass surface down there, a line at right angles to it is called the normal line, and we mark something called the angle of incidence between the incoming ray and the normal line. Now what's going to happen to that light ray? Well, a quick recap on refraction. If this was the crest of a wave, as it comes in, once it hits the glass, the light slows down. It travels more slowly in glass because glass is denser, and that slows the light ray down. So if this is my wave crest, it comes in, it slows down, but because it's coming in at an angle, this end here slows down first, this top end keeps going fast, and the light swings round and heads off down in this direction down here. And we call that effect refraction. Okay, so the rule is that light going from glass into air refracts towards the normal. Okay, the normal can be seen to be projecting downwards as well as upwards, and you can see there that the ray is bent, and it's bent towards this normal line. So remember the rule: light going from air into glass refracts towards the normal. Now we could measure these angles, and if we did an experiment, we could try a range of different angles here with maybe a light rays from a light box, a protractor here to measure the angles, mark the emerging light ray coming out of our glass block with maybe a mark on your paper, draw the lines, work out where the rays are, repeat a few times, measure some I's and R's, and then we'd start to think about the mathematical relationship. And you might think to start with that I might be proportional to R. It turns out that in fact the relationship is a bit different to that. The relationship is that sine I divided by sine of R is a constant, which we give the symbol n to, and this n value is called the refractive index. And the refractive index is a measure of how much the light slows down by. A refractive index, for example, of 2 would mean that it's slowed down to half its speed. So if the refractive index of my block was 2, then the light would be half as fast in the glass as it was in the air. And obviously that effect is what causes it to change direction. So the bigger the refractive index, the greater the shift in direction towards the normal. Typically for glass, the refractive index is usually around about 1.4, 1.42 would be a typical value for glass. So the n value for glass around about 1.42. So what I'd like you to do as a little exercise to see if you've got the hang of this is if I give you some values, just pause the video and see if you can work out the n value that goes with them. So let's imagine in my example that the I value was 50 degrees and the R value was 36 degrees. Okay, we've got our formula here which has a name, it's called Snell's law. Can you use Snell's law to work out the refractive index, the n value for this particular glass block? Remember, n values can change, so don't assume that it's going to be exactly the same as the one I used just a moment ago. What's the n value for this glass block if I is 50 and R is 36? Pause the video, have a go at it, then I'll show you how to do it. Okay, so we're going to try and work out our n value. So we've got I as 50, R as 36. It's fairly straightforward. Substitute into this equation. Sine I is going to be sine 50. Sine R is 36. And that's going to give us our n value. So if we do that on the calculator, we've got sine of 50, which is 0.766, and sine of 36 is around about 0.588. I'm just going to round that to the nearest decimal place there. So we do that on our calculator, 0.766 divided by 0.588, and we get a value of 1.3. Okay, so the n value for this is 1.3. N doesn't have any any units, it's just a factor, the factor telling us how much the speed of light has decreased by as it's gone from the air to the glass. Okay, so that would be one calculation we could do with Snell's law. Let me try you on one that's going to take a little bit more work. Let's suppose now that I have an I value and I want to work out an R value. So I'm going to have an I value of 50.0 degrees, and an N value, a refractive index, of 1.42. And the question is, what is R? What is the angle of refraction? Okay, I value of 50, N value of 1.42. Can you work out R? So again, pause the video, have a go, and then I'll show you how to do it. Alright, so in this case, we're going to have to do a little bit of rearrangement because our formula starts with sine R on the bottom, and we're going to try and work out what R is. So how am I going to go about that? Well, why don't I rearrange the formula to get sine I on the bottom and sine R on the top? So let's do a little bit of rearrangement. Well, if I multiply the equation both sides by sine R, then what I'll get is sine I is equal to N times sine R. Okay, I got that by, I multiply this side, I've got sine R divided by sine R, that will cancel to give me just sine I, and over here I've got N times sine R. And then if I divide both sides by N, I get sine I divided by N equals sine R. And now I could work out the sine R value, which is getting close to where we want to be. We want R, but at least that will get us to sine R. So let's put some numbers in. We've got sine of 50 divided by N, which is 1.42, and that will give us sine R. Okay, so we do sine of 50 again on our calculators. You might remember we did this a moment ago. That's 0.766 divided by 1.42, and that is going to be our sine R value. So that comes out as 0.539. How do we get back to R? That's a sine value. We want to get back to the angle. We want to get back to R. And the answer is we need to do inverse sine. So R is the inverse sine of 0.539. And we can do that on our calculator by pressing shift sign. And if we do shift sign of 0.539, we get 32.6 degrees. Okay? So virtually 33 degrees. So that's an example of going the other way with Snell's law.